So let's look at nuclear reactions now. From what we've already studied, we know that radioactivity is a natural occurring event. It happens when an isotope is unstable, occurring naturally in nature depending on certain isotopes. It, though, can also be created and controlled. And this is probably the type of reaction that you're most familiar with or think about the most, a controlled or created reaction in a laboratory setting. And what we use is we use what's called a particle accelerator to create radioactive material. What happens in a particle accelerator, and really this is just a big machine that speeds up the particles, the alpha particle or a neutron is actually aimed at the nucleus of an isotope. It is then absorbed and becomes an isotope that doesn't naturally occur. So here's a potential isotope that's been created. Aluminum 27, if we add an alpha particle to it and we send that alpha particle into that aluminum, notice the number of protons will become 15, 13 plus 2. This 30 comes from 27 and 4, but we have one other thing left over. And often in radioactive decay, we get these additional particles that occur. So we're going to look at these types of reactions. Now, if though an alpha particle is used, very, very high speeds are required. High speeds and energy are required to get that alpha particle into the nucleus. It has a positive charge. It takes a lot of work, a lot of energy. However, though, a neutron can actually be used at slow speeds. A neutron has no charge, and if it's fired at the nucleus, it will just get absorbed, becoming an unstable nucleus. And that unstable nucleus then spontaneously decays. It is radioactive. This type of radioactivity is called artificial radioactivity. We have created something artificially that is radioactive. What we've learned over the years is that radiation can really affect human beings. And what it actually affects is the DNA in our cells. If there is a low level of background radiation, like that comes from the sun, or short bursts of it, maybe you get an X-ray or exposed to some minor radiation, our body can actually repair that. It's the large-scale radiation, something like the gamma ray, that has a high burst of intense radiation that can actually damage DNA. And this is the DNA picture here. Alpha particle might hit your DNA and then it would be repaired. But gamma can really affect the DNA, and that's where we get all of these symptoms of exposure to radiation, or types of cancers, that kind of thing, because the DNA has actually been altered by this intense radiation. Now, during a nuclear reaction, large amounts of energy are released. And this is where we start to harness this energy, use it for our own benefit or potentially our own harm. This energy comes from the nuclear mass. Some of the nuclear mass, when it decays, is actually transferred into energy. And it was good old Albert Einstein that told us about this, that energy actually comes from mass. And he formulated the equation E equals mc squared, probably the most famous equation in science. And I suspect you have an idea that E stands for energy and M stands for mass, and in this case we're going to consider the mass lost. But what a lot of people don't realize is that the C value is really the speed of light. The speed of light, which is 3.0 times 10 to the 8 meters per second. A constant value that we're going to use for our calculations, a very, very large number. And because that's such a large number, and if we look at our equation, we're going to square that large number, it's going to get even larger. So just a small amount of mass can create a huge amount of energy. Let's put this into practice. Let's look at an example. If we could take a grain of sand, which has approximately the mass of 6.3 times 10 to the negative 5 kilograms, and take it all and convert it into energy. The question is, how many joules of energy are produced? And if you look over here, there's a couple references to what a joule is. Sitting quietly, average person, about 100 joules of heat per second. If you were moving a small apple, lifting it a meter, that's about 1 joule. So just to give you an idea of what a joule of energy is. Well, we start this out pretty straightforward. Our equation, E equals mc squared. All right. Our energy, our E, is what we're trying to find. We're going to take the mass, and the mass in this case is the mass of the grain of sand, 6.3 times 10 to the negative 5 kilograms. And we always want to make sure our mass is in kilograms. And C, again, C is that constant value, 3.0 times 10 to the 8 meters per second. Just plug it all into your equation. The mass is 6.3 times 10 to the negative 5 kilograms. And because we're multiplying, I'm going to fire that in brackets, times 3.0 times 10 to the 8. Let's make that a better 8 meters per second. And make sure we square that. And then all you have to do at this point is just fire it in your calculator and get your number, which is 5.67 times 10 to the 12 joules. A huge amount of energy. So you can just imagine a single grain of sand can produce that amount of energy. It's a huge release in a nuclear reaction. And we're going to look at these nuclear reactions and their energy and the use of their energy as we go further through this topic.